When we studied groups, we also studied group homomorphisms. They were functions between groups that preserved the group operation. Similar to that, there's the notion of a ring homomorphism. So suppose you have two rings R and S. Then a ring homomorphism is a function phi from R to S, which basically preserves all the structures that are involved in the definition of a ring. Namely, it preserves addition and multiplication. So firstly, we assume that phi of A plus B is phi of A plus phi of B for all A, B in R, and it preserves multiplication. Phi of A times B is equal to phi of A times phi of B for all A, B in R. We also make one more assumption. So now, because phi is a group homomorphism, it takes the additive of the additive group R. That's what axiom 1 says. It takes 0 to 0. Okay, but R with multiplication is not a group because, for example, elements need not have inverses. And so you cannot argue that phi takes the multiplicative unit 1 of R to the multiplicative unit of S. So we need to add that as an axiom. Phi of 1R, by this I mean the unit element of R, is taken to the unit element of S. And this is not automatic. For example, if you take R and S to be any rings, and you take phi of x to be 0 for all x in R, then this will satisfy 1 and 2, but it will not satisfy 3. Okay, and we can talk about isomorphism. An isomorphism of rings is a bijective homomorphism. And if phi from R to S is an isomorphism, then phi inverse from S to R is also an isomorphism. Okay, let's look at some examples. So we had the group Z, and we had the group Z mod NZ, and while studying groups, we had seen that the homomorphism which takes X to X mod N, the residue class of X mod N, which I can write as X plus NZ, is a group homomorphism, but this is also a ring homomorphism. Because residue classes are respected under addition and multiplication, and the residue class of 1 goes to 1. Okay, let's look at a slightly more interesting example. Take the ring of polynomials in some field x. So this is the set of all polynomials in the variable x with coefficients in the field f. And you can define a function from f of x to f by just taking the polynomial f of x to f of a for some fixed a. So let's say fix a in f. For some fixed a in f. And this is going to be ring homomorphism. And similar to this, oops, why have I called this 3? This is example 2. And example 3, you can go from 2 variables to 1 variable. So you can define a homomorphism from f of xy to f of x by just putting f of xy goes to f of x comma a. Now this a is fixed and x is still a variable, so this is a polynomial in one variable. This is also a ring homomorphism. Okay, consider the ring. You take the ring of polynomials in a variable x, and then you take the ring of polynomials in another variable y whose coefficients are polynomials in x. Okay, so an element here looks like p0x plus p1x times y plus p2x times y squared and so on, plus pnx times y to the n, where p0x dot 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 up to pnx belong to fx. And this is a ring, and then you can expand this out. So you have this, suppose pix is equal to ai0 plus ai1x plus ai let's say mi x to the power mi. Then you can write pix y to the I as ai0 y to the power I plus ai1 x y to the power I plus dot 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 plus ai mi x to the mi y power I. So each of these products here will become a polynomial in two variables x and y, and you add it up, and this is actually a polynomial in x and y. So it turns out, so what this means is that you can think of a polynomial in y whose coefficients are polynomials in x as a polynomial in x and y. And so what we are saying is that the ring is isomorphic to polynomials in two variables f of x comma y. The isomorphism is defined by just expanding out these coefficients and getting polynomials in two variables. So this is an example of a ring isomorphism. Okay, another example of a ring isomorphism would be, so we've seen that z mod mz and z mod nz, if m and n are co-prime, then this is isomorphic to z mod m and z if m and n are co-prime. And this was the Chinese remainder theorem. But this is also a ring isomorphism. Just go back and check how we constructed this isomorphism and verify that it preserves, in addition to the addition, also the multiplication and units. And a last example, just take zx to z mod nzx. Polynomials with integer coefficients to polynomials whose coefficients are integers mod n. So you take a0 plus a1x plus an x to the n goes to a0 bar plus a1 bar x plus an bar x to the n, where ai bar is ai plus nz, the residue class of ai mod n. Okay, so with that we have seen the definition of ring homomorphism, the notion of ring isomorphisms, and we've seen some examples.